Good morning. Today we're going to learn lesson 6.1. We have chapter starting chapter 6, discrete and continuous random variables. So a probability model describes the outcomes of a chance process and the likelihood that those outcomes will occur. So two things, outcomes and likelihood that those will occur. So for example, suppose we toss a fair coin 3 times. The reason I say fair coin because fair coin has a chance 50-50 to be heads or tail versus if you have a weight coin, that type of a coin might not have a 50-50 chance. So when we talk about random selection, we always talk about a fair coin. So we toss a coin uh, 3 times, and so we need to list all possible outcomes. So my first toss, first time I toss a coin, of course I have my choice of heads or tail. And then if I toss the coin the second time, my choice is also again heads of tail. And if I toss the coin the third time, each time I have a heads of tail. So if I'm listing all possible outcomes, my first choice would be heads, heads, heads. Then heads, heads, tail. Then heads, tail, heads. Heads, tail, tail. Tail, heads, heads. Tail, heads, tail. Tail, tail, heads. And tail, tail, tail. I have 1, 2, 3, 4, 5, 6, 7, 8, and each one has a chance of 1/8 occurring. So since there are 8 equally likely outcomes, so 8 equally likely outcomes, the probability is 1/8 for each possible outcome. If we define the variable x as the number of heads obtained, the value of x varies from one set of tosses to another. So my variable is defined by number of heads that we roll. So my possible outcomes are 0, 1, 2, and 3, meaning I can have 0 heads, 1 head, 2 heads, or 3 heads. So how likely is x to take each of those values? It will be easier to answer this question if we group the possible outcomes by the number of heads obtained. So 0 means that I have all 3 tails. If I get 1 head, that means I would have head, tail, tail choice, tail, heads, tail choice, or tail, tail, heads choice. To get 2 heads, my choice can be heads, heads, tail, heads, tail, head, and tail, heads, heads. And then, of course, to get 3 heads, I only have 1. Heads, heads, head. So the probability of rolling 0 is 1/8. Rolling 1 head, tossing 1 head, you get 3/8. 2 is 3/8, and getting 3 heads is 1/8. So my probability for each event. The figure below shows the probability distribution in graphical form, and notice the symmetrical shape. So if I take my pencil and draw the line, I will notice the symmetrical shape. We can use the probability distributions to answer questions about the variable x. What is the probability that we get at least 1 head? So at least 1 head in 3 tosses of the coin. In symbols, we want to find probability x is greater or equal to 1. We could add the probabilities to get the answer. Notice the notation. On the test, you have to show the notation to get full credit. So probability of x is equal to 1 plus probability of x is equal to 2 plus probability of x is equal to 3. So probability of x is equal to 1 is 3/8. 2 is 3/8, and 3 is 1/8. So my answer is total of 7/8. Okay, that's one way of finding the probability. And the second way is to use what we learned last chapter. That's the complement rule. It doesn't matter which method you use as long as you're clear on your labeling and your notification. So probability of x is greater or equal to 1. We can use the complement. So of x is less than 1 and subtract it from 1. So that would be 1 minus probability of x is equal to 0. And in this case, 0 is 1/8. So 1/8 1 minus 1/8. So my answer is still 7/8. So I got the same answer. So again, it doesn't matter which method you use as long as you're consistent and show your work by the proper labeling. A numerical variable that describes the outcomes of a chance process, like x in tossing of a coin, is called a random variable. The probability model of a random variable is its probability distribution. So random variable takes numerical values that describe the outcomes of some chance process. Probability distribution gives the possible values and probabilities of a random variable. The first one we're going to talk about is discrete random variable. So discrete random variables, we have learned several rules for probability, but only one way of assigning probabilities to the events. We assign a probability to every individual outcome, then we add these probabilities to find the probability of the event. This idea works well if we can find a way to list all possible outcomes. Okay? We will call random variables having probability assigned this way discrete random variables. So one more time, if we can list all possible outcomes, it would be discrete random variables. The probability distribution for a discrete random variable must have outcome probabilities that are between 0 and 1 and they add up to 1. So these two requirements have to be met. Okay, so one more time, discrete random variables and their probability distributions. So a discrete random variable takes a fixed set of possible values. The probability distribution of a discrete random variable lists the values and their probabilities. Notice that notation and the probability is written P of x and then P1 through Pk. The probabilities must satisfy two requirements. So here are your two requirements. You always have to verify that those two rules are satisfied. To find the probability of an event, we add the probabilities of particular values of x that made up that event. So the first example, we're going to talk about Apgar scores of a health at birth. In 1952, Dr. Virginia Apgar suggested 5 criteria for measuring a baby's health at birth: skin color, heart rate, muscle tone, breathing, and the response when stimulated. She developed a scale to rate the newborn on each of the 5 criteria. A baby's Apgar score is the sum of the ratings on each of the 5 scales, which gives a whole number value from 0 to 10. Apgar scores are still used today to evaluate the health of the newborn. So I don't know how many of you know your Apgar score, but when you were born, your mothers and fathers were given your score. So when baby is born, they take the baby away right away. They do all the measurements and evaluations, and then they give baby back to the mother. So everybody is given that score. What Apgar scores are typical? To find out, researchers recorded an APGAR score of over 2 million newborn babies in a single year. Imagine selecting one of these newborns, at random. That's our chance process. So we define the random variable X as the APGAR score of a randomly selected baby 1 minute after the birth. This table lists the probabilities. Sorry, it's kind of squished. You need to read it up and down. And notice that it's 0 point something. So make sure that you always include the 0. So the first question is, show that the probability distribution for X is legitimate. So the first rule is that every probability is a number between 0 and 1. So we go look at the table and notice that each one of those is a number between 0 and 1. So we are going to put number 1, probability for each outcome is between 0 and 1. The second thing you need to do is you need to add all the probabilities, and they all have to add up to 1. So I'm not going to add all of them. I'm going to add them all on a calculator. But when I'm listing them, I'm just going to list the first two. And by the way, that's a common thing to do, just to list first two, dot, dot, you list the last one, 0.053, and they all add up to 1. And so on the test, they assume that you add them all up, but you don't have to list all of them. You would list first two, dot, dot, and the last. So you would say the probability is distribution does satisfy the two rules. The next thing, we're going to make a histogram of the probability distribution, and they want us to describe what we see. So the first thing is I'm going to have my probability. And I'm going to have my APGAR score. And if you look at the numbers, notice that my values go from 0 to 10. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And probability is super small and goes the highest, it goes 0.4. So we can go 0.1, 0.2, 0.3, and 0.4. So for the 0, it's super, like barely above, barely above, barely above. 3, still barely above. 4, kind of moving up. 5, going a little up. 6, going a little up. 7, getting closer to 0.1. 8 is 0.3. Oops, 0.3. 0.9 is 0.4. And then 10 goes back to halfway between 0.1. So how would you describe if you take your pen and then you outline? What do you notice? You would hopefully notice that it is skewed which direction? Left. And you need to make a comment. You need to make sure that you explain that most of the babies are testing at a higher end of the scale. So most of the babies are testing at the higher APGAR scores, and especially between 8 and 9. Okay, so that's what means skewed left. The most of the data is located to the right. Doctors decided that the Apgar score of 7 or higher indicates a healthy baby. So 7 or higher indicates a healthy baby. What is the probability that the randomly selected baby is healthy? So in this case, we need to write the probability that the baby is healthy would be probability of x is greater or equal to 7. That means I'm looking for the probability of x is equal to 7. Probability of x is equal to 8. X is equal to 9. And probability of x is equal to 10. So go ahead and add all those probabilities. So that would be 0.09, 0.319, 0.437, and 0.053. When you add them all up, you get 0.908. Now, I want to emphasize every year it happens, you guys don't pay attention to detail. Probability of randomly selecting newborn whose score is greater than or equal to 7 is not the same as probability of the baby score greater than 7. Please, please, please pay attention to this. This is something that every year students lose points because they don't read carefully. So here I get about 91%. Versus if I just make a mistake, I make it greater than 7, so that means it would be x is equal to 8, x is equal to 9, x is equal to 10, and so I would have 0.319, 0.437, and 0.053. And by the way, I suggest that you write the decimals, write the 0 in front of the decimal so you don't make a mistake. And so that would be 809. So 81% versus 91%. So make sure that you always, always, always pay attention to what information do they give you and what do you need to use. Okay. Next thing, we're going to talk about expected value of a discrete random variable. When we analyze the distribution of a quantitative data in Chapter 1, we made it a point to discuss shape, center, and spread, and identify any outliers. We will follow the same strategy with probability distributions of random variables. You can use what you learned earlier to describe the shape of the probability distribution in a histogram. We've already seen example of symmetric, number of heads in 3 coin tosses, and left skewed Apgar score at a randomly chosen baby. Probability distributions. What about center and spread? So the mean of x or x bar of a set of observation is their ordinary average. The mean mu of x over discrete random variables is also an average of the possible values of x, but with an important change to take into account that the fact that not all outcomes may be equally likely. Okay, so all outcomes are not equally possibly likely. Simple example will show what we mean. So winning and losing at roulette, finding the mean of a discrete random variable. On an American roulette wheel, there are 38 slots numbered 1 through 36 plus 0 and 0, 0. Half of the slots from 1 to 36 are red, the other half are black. Both 0 and 0, 0 are green. Suppose that a player places a simple $1 bet on red. So $1 bet on red. If the ball lands on a red slot, the player gets the original dollar back plus, so he gets the original dollar back, plus an additional dollar for winning the bet. If the ball lands in a different color slot, the player loses the dollar bet to the casino. Okay, so let's define the random variable x net gain from a single dollar bet on red. So x is the net gain from a single dollar bet on red. The possible values for X are either he earns a dollar or he loses a dollar. The player either gains a dollar or loses a dollar. What are the corresponding probabilities? The chance that the ball lands in a red slot is 18 out of 38. Okay, so half of the slots are red, so that's going to be 18 out of 38. The chance that the ball lands on a different color slot, it is 20 out of 38. Okay, so it's either black or green. Created the probability distribution for X. So we are going to create, we have outcomes, we have value X, and we have probabilities. So we have value X, we have probability, and we have outcomes. So either we have he loses a dollar, or he gains a dollar, and the probability that he loses a dollar is 20 out of 38, and that he wins is 18 out of 38. What are the players? What's the player's average gain? The ordinary average of the two possible outcomes, minus a dollar and plus a dollar, is 0. But 0 isn't the average of the winnings because the player is less likely to win than to lose. In the long run, the player gains a dollar 18 times on every 38 games and plays, and loses a dollar on 20 out of 38 bets. So the player's long run average gain for this simple bet is, so we are looking for the mu of X. So the average of X is equal to, I lose a dollar times 20 over 38 plus win a dollar, which is 18 out of 38. So if I have minus 20 out of 38 plus 18 out of 38 is negative 2 out of 38, which is negative 1 out of 19, and changes into decimal is approximately negative 0.05. Okay, so you see that in the long run, okay, in the long run, the player loses and the casino gains negative 0.05 per bet. Okay, we're talking about not one toss, we're talking about in the long run. If someone actually played several games of roulette, we could call the mean amount the person gained. The mean is the previous, in the previous example, is a different quantity. It is the long run average gain we'd expect if someone played roulette a very large number of times. So I'm not talking about 1, 2, 3. I'm talking about thousands and thousands of times. So this is over a long period of time. For this reason, the mean of a random variable is often referred to as its expected value, because it's considered over a long period of time, and so the long average is called also the expected value. Just as probabilities are in idealized distribution description of long-run proportions. The mean of a discrete random variable describes the long-run average outcome. There are two ways of denoting the mean of a random variable. Okay, so there's two notations, and on the test, they will write them either way. You need to recognize that they mean the same thing. So we can use the notation nu of x, or we can write e of x, which is expected value of x. So notice my notation. Both of them mean the same thing. The mean of any discrete random variable is found just as in the roulette example. It is the average of the possible outcomes by a weighted average in which outcome is weighted by its probability. So taking into consideration the probability of each outcome, you add and find the average of those. So mean expected value of a discrete random variable. So suppose that x is discrete random variable. Notice my distribution, notice the notation. You will need to be able to list it that way. So to find the mean of expected value, you multiply each possible value by its probability and then all the products. So this formula is given to you on a formula sheet. So you multiply each possible outcome and then you add it together. Okay, so here is my APGAR score. What is typical? In our early example, we defined the random variable x to be the APGAR score of a randomly selected baby. The table below gives the probability distribution of x once again. So they want us to complete the mean of the random variable x and interpret this in the context. Okay, so we need to list all of them. And so to find the mean, you would write, you would write mu of x, or we can also write it as e of x equals to 0 times 0.001 plus 1 times 0.006 plus 2 times 0.007 plus 3 times 0.008 plus 4 times 0.012, 5 times 0.020, 6 times 0.038, 7, 0.099, 8, 0.319, 9, 0.437, and 10, 0.053. You add them all together and you get your mean, and your mean of x is equal to 8.128. So a mean average APGAR score for a randomly selected baby is 8.128. Notice that mean score of 8128 is not a possible value of the random variable x. It is also not an integer. If you think of the mean as a long-run average over many repetitions, this fact shouldn't bother you. So notice that I do this over a long period of time. So it's over long averages and many repetitions. Okay. Standard deviation and variance of a discrete random variable. With the mean as our measure of center for discrete random variable, so mean is the measure of center for discrete random variable, it shouldn't surprise you that we use the standard deviation as our measures of spread. In chapter 1, we have defined the sample variance as S standard deviation squared, so average squared deviation from the mean, and then took the square root of the variance to get the same sample standard deviation S of x. So the definition of a variance of a random variable, notice it's sigma squared, is similar to the definition of the variance for a set of quantitative data. That is, the variance is an average of the square deviations of the values of x from its mean, which is mu. As with the mean, the average we use is a weighted average in which each outcome is weighted by its probability to take account outcomes that are not equally likely. That's important. So to get the standard deviation of the random variable, we take the square root of the variance. So here are your details. Variance and standard deviation of discrete random variable. Mu of x is the mean of x. The variance of x is labeled as standard deviation of x squared, and you find the difference between the value and the mean. This formula is also given to you in a formula sheet, and you don't have to have it memorized. The standard deviation is the square root of the variance. So the standard deviation of a random variable x is a measure of how much the values of the variable tend to vary on average from the mean, which the definition has not changed. It's the same what we have been using. You have to be able to, this is what you have to always explain in an answer. Okay? Always, always, always. You need to define that. Okay, let's look at the example. So, calculating the measures of spread. In the last example, we calculated the mean APGAR score of a randomly chosen newborn to be 8.128. The table below above gives the probability distribution for x. Compute and interpret the standard deviation of the random variable x. So we are going to go ahead and we're going to calculate the value, and the first thing we're going to do is we're going to set it up. So the standard deviation, so sigma of x squared, that's my variance. You're going to take the first one and subtract the mean and square it and multiply by the probability. So to list it, you would go 0 minus 8.128 squared times the probability, which is 0.001. Then you add to this the second one, which is 1 minus 8.128 squared times the probability of the second one. 2 minus 8.128 squared times the probability, which is probability 0.007. 3 minus 8.128 squared times 0.008. 4 minus 8.128 squared times 0.012. 5 minus 8.128 squared times 0.020. 6 minus 8.128 squared times 0.038. 0.099. 8 minus 8.128 squared times 0.319. 9 minus 8.128 squared times 0.437. And then the last one, 10 minus 8.128 squared times 0.053. If you add all these up and calculate, you will get that the sum, the variance of standard deviation is equal to 2.066. And to find the standard deviation, you would take the square root. So standard deviation is equal to 1.437. 1.437. So to interpret it, you would use your definition from the previous page. It says that the standard deviation of a randomly chosen infant tells us how much the value of the variable tends to vary on average from the mean. So a randomly chosen infant's APGAR score tends to vary by 1.437 on average from the mean score. Okay. Continuous random variables. So there are certain specific rules for continuous random variables. Continuous random variables, when we use the table of random digits to select a digit between 0 and 9, the result is a discrete random variable. The probability model assigns probability 1 to 10 to each of the 10 possible values. The figure below shows the probability distribution of that random variable. Okay? So we have probability, we have a value, and notice that each one of my probability is the same. Suppose we want to choose a number at random between 0 and 1, allowing any number between 0 and 1 as the outcome. Calculated and computer random number generator will do this. The sample space of this chance process is the entire interval on numbers. So all numbers between 0 and 1. We call the outcome of the random number generator Y for short. How can we find the probabilities of 0.3 to 0.7? As in the case of selected random digits, we would like all possible outcomes to be equally likely. But we cannot assign probabilities to each individual value and then add them because there are infinitely many possible values. So when we have infinitely many possible values, we call those continuous random variables. In a situation like this, we use a different way of assigning probabilities as areas under the density curve. So from chapter 2, we talked about density curves, and we already said that the area exactly underneath the density curve is always probability of 1. So random numbers, density curve. The random number generator will spread its output uniformly across the entire interval from 0 to 1 as we allow it to generate a long sequence of random numbers. The results of many trials are represented by the density curve of a uniform distribution. The graph has height of 1 over the interval from 0 to 1. The area under the density curve is always equal to 1. And the probability of any event is the area under the density curve and above the event in question. So the figure below shows the probability that the random number generator produces a number y that's between 0.3 and 0.7. So we are looking at the area between 0.3 and 0.7. My density curve, remember the height is 1, and so that because the area under the shaded rectangle, remember we are looking at the length times width, 0.4 times 1 or 0.4. We call y continuous random variable because its values are not isolated numbers, but intervals of numbers. There's infinitely many possible solutions, possible numbers that we can use. So continuous random variable takes all values in an interval of numbers. The probability distribution is described by a density curve, and the probability of any event is the area under the density curve and above the value of x that marks that event. So this is your definition. So the probability distribution for continuous random variables assigns probabilities to intervals of outcomes rather than to individual outcomes. So in previous, each score had its own probability. Here we have a continuous outcomes. All continuous probability models assign probability 0 to every individual outcome. This is super important. So every individual outcome has 0 as an outcome. Only intervals of values have positive probability. To see that this is true, consider a specific outcome from the random number generator of the previous example. So for example, we want the probability y equals 0.7. The probability of this event is the area under the density curve that's above the point 0.7 on the horizontal axis. This vertical line height segment has no width, so the area is 0. So 0.7 is exactly 0.7. There's no width. And because there's no width, your width is 0. So it would not have the probability. So for that reason, we always we can write is less or equal to or just less. It doesn't make the difference. So the answer is just 0.4. So remember how in discrete probability, it absolutely does matter if you write it as a less or equal. In the continuous random variables, we do not make a distinction between. So we can use any density curve to assign probabilities. The density curves that are most familiar to us are normal curves. Normal distribution can be probability distributed as well as description of data. There's a close connection between normal distribution as an idealized description for the data and a normal probability model. The following example shows what we mean. The young women and heights. Normal probability distribution. The height of young women closely follow the normal distribution with mean of 64 inches and standard deviation of 2.7 inches. This is a distribution for a large set of data. Now choose one young woman at random. Call her height y. If we repeat the random choice very many times, the distribution of value of y is the same normal distribution that describes the height of all young women. Find the probability that the chosen woman is between 68 and 70 inches tall. So the first thing we're going to do is we are going to create a visual. You have to graph the curve. And so the first thing we are going to do is that's what we're going to plot. And so you always have to graph the normal distribution curve. So we're going to number, oops, sorry, my line is not the best. And so my mean is 64, and I'm going to move on each side. I'm going to subtract and add one standard deviation. So adding one would be 66.7. Subtracting one standard deviation is 61.3. Then I'm going 2 standard deviations. And so that would be 69.4 and 58.6. And then 3 standard deviations would be 55.9 and 72.1. So if I'm drawing, this is my okay. So this is approximately my normal distribution. They want to know what is the probability that's between 68, so 68 and 70 inches tall. So that's somewhere here. Okay, we want to know that probability. So now we are going to standardize the z-scores and use table A for shaded area. So standardize z-scores and use table A for shaded area. Okay, so those of you who are learning standardization, you're in good shape. You need to know that the z-score is x minus mu over the standard deviation. Notice my notation, mu and sigma this time. It's not x bar, it's mu and sigma. So we are looking, we're going to standardize both scores. So the first score is going to be, let's see, what do I have? 68 and 70. So it's going to be 70 minus 64 divided by the standard deviation, which is 2.7. So my z-score is 2.22. And so I'm going to find the p-value of z-score that's less than 2.22. So that's your p-value in the table, which is going to, so from table, look up 2.22, you will find that it's 0.9868. Then you're going to find the z-score for 68. And the z-score for 68 is 1.48. So the p-value from z-score that's less than 1.48, because remember the table always gives you the area to the left, it's 0.9306. Okay, 0.9026. So we are looking for the value. So we would make a notation here. So I'm looking for the p-value of 148 is less or equal to z, which is less or equal to 2.22. So if I'm looking at the shaded part, I'm looking at 70 to the left, right? That's your 2.22, which is 0.9868 minus the p-value of the 68, which is z-score of 148, and has a p-value of 0.9306. So you subtract this from this, and you get the difference, okay? So you would write p-value of z that's less than 2.22 minus the p-value of z that's less than 1.48. It's the difference. So you would have 0.9868 minus 0.9306 is 0.0562. So to answer the question, find the probability that chosen woman is between 68 and 70 inches tall. My probability would be approximately 5.6%, or probability would be approximately 6%. So the calculations in preceding example is the same as it did in chapter 2. So the steps, the same. Notation, different. Okay, because here, notice that I'm using mu and sigma, and previously we used x bar and s. What about the mean and standard deviation for continuous random variables? The probability distribution of a continuous random variable x is described by density curve. The chapter 2 showed how to find the mean and distribution of the distribution. It is the point at which the area under the density curve would balance if it were made out of solid material. The mean lies at the center of symmetric density curves such as normal curves. We can locate the standard deviation of a normal distribution from the inflection points. Remember, the inflection point was exactly where where it would start moving, wherever the standard deviation is. So when it would start slanting, that would be the inflection point. So you need to know that. Exact calculation of the mean and standard deviation for most continuous random variables requires advanced mathematics, and you will not be required to calculate it. You will be using the calculator here. Okay, so this is what you need to know about continuous, and what you need to know about discrete random variables. You need to know when do you use, you need to know how to describe them, and you need to know how to set it up. Okay, how to calculate. Okay, hopefully that was sufficient. If you guys need to look at this again, please do so. The next is 6.2, which we're going to do the next time, and the homework is on your assignment sheet.